Rates of reaction. Unit C2, Section 4. The main areas in this section are how to measure rates, interpreting data given in an exam question, stating how the rate of reaction will change if the conditions are changed, and explaining these changes using collision theory. Rates can be measured by comparing the amount of product made, or reactant used up, to the time taken for this change to happen. More product made in the same amount of time is a faster reaction, or the same amount of reactant used up in a shorter time is a faster rate of reaction. Don't forget to include the time taken for the change to happen. More product made doesn't mean that the reaction is faster, it might just have been left for a longer time and so made more product. In some exam questions, you are asked to describe what you would see when a chemical reaction happens. Remember, you don't need to learn lots of different reactions, that would be bonkers, but there will be information given in the question to help you. In this example, the state symbols show you that there is a solid at the start, but not at the end, and that a gas is made. You could then say that the magnesium carbonate dissolves and fizzing would be seen. If you are asked what would be seen, don't write an equation. You are very unlikely to see an equation floating in a beaker. Sometimes the question will give an observation and ask you to explain it. For example, why is there fizzing when magnesium carbonate is added to hydrochloric acid? Again, use the equation to help you answer. The reaction makes carbon dioxide gas, and so the bubbles are carbon dioxide gas being given off. It's quite common to use graphs to show rate of reaction, and there aren't many other places in Unit 2 where graphs show useful chemistry. Many of the graphs in exam questions show how the amount of reactant or product changes during an experiment. In this case, the volume of gas collected has been measured as the reaction has happened. You should be able to recognize that the steeper the line, the more gas is given off every second, and so the faster the rate of reaction. If the amount of reactants is the same, then the amount of products will be the same too, and so the end point on the graph will be the same, although you might get to the end point a bit sooner or later. If you are asked to draw a new line on the graph, think, is the reaction faster or slower? Is the line going to be steeper or more shallow? Are the amounts of reactants the same, or twice as much, or half as much as they were originally? This will tell you if the line is supposed to end at the same place, or make twice or half as much. And if you are asked to describe the shape of the graph, there are three key things to say. The graph goes up steeply at the start, the graph gets less steep as time goes on, it levels off at 50 centimeters cubed of gas. Don't explain why the changes occur unless you are asked to. There are 4 factors that affect the rate that you need to know about. To explain them, you need to use collision theory. Collision theory. Particles must collide to cause a reaction. The more frequently they collide, the faster the reaction is. Anything that increases the frequency of collisions will increase the rate of reaction. Surface area only applies to solids, because when we have a solid, the only particles that can collide with something else are the ones on the surface. In my lump of 36 particles, only the 20 on the outside could react. Cutting the lump into 4 smaller pieces means that in total there are more particles on the outside. Now there are 32 particles on the outside. Remember, for a fair test, you can only change one variable. You must have exactly the same mass if you are going to see how the rate changes with different surface area. Concentration of solutions and pressure of gases measure the same thing. That is the number of particles in a set volume. In a solution, most of the particles are water molecules, and there will be particles of the other chemical spread out between some of the water molecules. A high concentration means that there will be more particles per litre of water. I haven't shown the water molecules in these diagrams so that you can see the acid particles more clearly. The more particles there are in a set volume, the more frequently they will collide, and so the faster the rate of reaction. And this is true for solutions and gases. Increasing the temperature of the chemicals also increases the rate of reaction. Heating particles makes them move faster. To be fair, if someone started heating you with a Bunsen burner, you would move faster too. But it makes the particles move faster, so they're going to collide with each other much more frequently. If they are moving faster when they collide, they hit each other with more energy. In other words, they hit each other harder. Particles need to hit each other hard enough to cause a reaction, and the faster they are moving, then the more of the collisions will cause that reaction. Catalysts are very important in speeding up chemical reactions, but you don't need to know much about them for the C2 module. Catalysts speed up chemical reactions, but they aren't used up themselves. Some books say that they don't change or react, but this isn't quite true. They are unchanged at the end, though. Catalysts are often used in industry because they will be able to make more product in the same amount of time, or they might be used to get the same rate of reaction but at a lower temperature, and both of these will reduce costs. You do need to know a few examples from other parts of the specification, for example nickel being used to help harden vegetable oils from the C1 module. How they actually work is covered in the energy module in C3. That covers rates of reaction. Next stop is exothermic and endothermic reactions.